Hello, my name is Darren Thomas. I am the Director of Educational Research Techniques. In this video, we're going to take a look at how to multiply radical expressions. So let's begin. Alright, so when we're dealing with a radical expression, we're dealing with something with an index, a radicand, and a radical, if you will. And so we're going to multiply these. So let's take a look at our first example here. Let's say that I have 3 times the square root of 2 times 2 times the square root of 30. Now the beautiful thing about multiplying radicals, is that you just multiply like terms and that's it. So to make this simple, basically what we're going to do is we're going to get 3 times 2 here, which is going to give us 6, and then the square root of 2 times the square root of 30, which is going to equal the square root of 60. Now we're not quite done because we can, of course, simplify this square root of 60. And there's lots of ways to do this, but one way to do it is as follows. If I break this down, I would have the following. I would have 6 times the square root of 4 times the square root of 15. Now, why did I do that? Because 4 times 15 gives me 60. But another beautiful thing is this. 4 is a perfect square. So when I reduce that, I get the following. 6 times 2 times the square root of 15. And when all things are said and done, the final answer will be 12 times the square root of 15, because it's going to be very difficult, basically impossible, to further simplify the square root of 15. So this is our answer. And of course, this carries on if we have a slightly different radical, if you will, or different index. Different index is what I meant to say. So let me show you an example with a different index. So let's say I have 2 times the cube root of 18 times 3 times the cube root of 6. So of course the first thing I do is I just multiply everything straight across, and I end up with 6 times the cube root of 108. And so now I need to address this 108. I need to simplify this. So what I can do now, when I do this, I need to be looking for perfect cubes, if I will, because that way I can simplify it to the maximum. So this is what we get. If I were to factor this in the most simplistic way, it would be 6 times the cube root of 27, this is a perfect cube by the way, times the cube root of 4. 27 times 4 will give me 108. But the beautiful thing is as follows. This right here simplifies to the number 3. So I end up with 6 times 3 times the cube root of 4, and then the final answer will be 18 times the cube root of 4. That's what we get. And so you can see how we were able to simplify that by following a very, very basic process here. Now let's do one. This last one is going to involve several things we haven't looked at. It's going to have variables, and it's going to have different exponents inside the example. Before I talk about it, let me just show it to you. It's easier to show you rather than do the theoretical side of it. So here it is, and it's messy. So hold your seats. 6 times 6 to the x squared times 8 to the square root of 30x to the 4th power. Now, there are many ways that this can be done. What I want to do is I want to try to show you as many steps as possible from start to finish, rather than taking any shortcuts, because I'm somehow more comfortable with math than, say, the people who may be watching this video. So the first thing I would do, and again, we're never going to dare say this is the only way to do it, but the first thing I would do is I would combine like terms, like always. So 6 times 8 is going to be 48. We've seen that before. Times 180 to the 6th power, like so. Now, what I need to do now is, that's not what I do first. Let me back up. Okay, what I really want to do first is I want to split apart these two radicals that I have. That's what I want to do. So I made a mistake there. So normally what we do is we do 6. I would do the 6 is going to be times the square root of 6 times x squared. That's the first thing I would do. All right, and then of course I'm going to have to finish that. I'll just put parentheses over here for the sake of completing this. And then I would do the same thing over here. I would do 8 times the square root of 30 times x to the 4th power. That's what I would do. And so when you do this, you can see that what's going to happen is that here, this square here and the square root here are going to eat each other. So you're going to be left with x. So I'm going to be left with 6 times x times the square root of 6, like so over here. And then the same thing is going to kind of happen over here. 2 of these numbers are going to disappear when we get rid of that. So it's going to go from x to the 4, x to the 2. So there's going to be, let's see here. It's going to be 8 times x squared times the square root of 30. That's what we're going to do here initially. This is what I wanted to do first. Now that we simplified this, because we have all the x's next to the constants now rather than inside the radicand, if you will, we combine like terms. And so we get 48, let me give you another color here. 48 x to the 3rd times 180, because 6 times 30 is 180, and 6x times 8x squared is 48 cubed, basically. Now, the next thing that I would do is that I now need to simplify this 180. I'm not done with that yet. I need to simplify this guy right here. He's my problem. Right here, this guy right here. And so there are many different ways to deal with this. But the good news is I have all my variables together. All the x's are together. That makes it easier for me when I'm trying to process these things. So if I wanted to do this now, this is what I would do. I have 48 x to the 3rd. That's the same. Now times 9, okay, times the square root of 9, times the square root of 4, times the square root of 5. That's what we're doing here. Now, why do we do this? We need to find something that when you multiply them all together, it comes up to 180. But whenever possible, you want to find perfect squares. So if I square root 9, I'll get 3. If I square root 4, I'll get 2. These are perfect. Can't do anything about 5. It's going to be the same. And so what happens now is that I have the following. If I continue with this thought process, I have 48 x to the 3rd times 3 times 2 times the square root of 5. And if I complete it, 48 times 3 times 2 is 288 x to the 3rd times the square root of 5. And that's how you get the answer. Again, this is not the only way. This may not even be the most efficient way to get the answer. However, I just kind of want to walk you through the cleanest process for me in order to find the answer in this particular situation. So let me review what we've gone through, and then I will conclude the video. So in this video, we looked at how to multiply radical expressions. And so basically all you do is you multiply like terms. So in this example up here at the top, we had a constant up here, then we had a radical and a radical here. You just multiply them, and then when possible you simplify, and that's pretty much how you get the answer. It's not that complicated, but you have to be able to find the patterns in terms of how can I factor, my radicals so that I start getting these perfect squares or these perfect cubes or whatever. That's the tricky part. And again, when you have something besides an index of 2, when you have an index of 3 or 4 or 5 or whatever, it's the same process. But now you have to make sure you find perfect cubes or perfect fourths or whatever it is, so that you're able to find the simplest answer when possible. And in this last example, we added the idea of variables there, and we also have different powers, x squared, x to the 4th or whatever, and all these other crazy things going on. So the first thing that we did in this example, because of the complexity, was we separated out the terms inside each parentheses, and then we dealt with things accordingly. So over here I did 6 times the square root of 6 times x squared. I separated all these terms here into their own little spaces in order to eliminate things whenever possible. And then, of course, yes, I did recombine them once everything was cleaned up. So after I separated them, I recombined them for my own purposes. I'm not going to claim this is the only way to do this. And then once everything was cleaned up, and what I mean by cleaned up was that everything outside the radical was as simple as I could make it, I then refocused my attention here on the stuff inside and was able to factor that out and get the final answer at the bottom. So I hope that this video was useful for you and that you were able to try to understand and follow what was happening. It's not that complicated if you kind of know what to expect and where things work and how things work out. And this can be very beneficial for you. So, my name is Darren Thomas. I am the Director of Educational Research Techniques. Take care.